The second semester of a college physics course is often referred to as electricity and magnetism, since these are the two subjects we will cover in detail. In the first 3 chapters this semester, we have studied electricity and the properties of electric fields that are created by stationary charges. Now we turn our attention to magnetism. And, just like we discovered a force exists between charged objects, we will find that a force also exists between magnetized objects. However, we will see that the electrostatic force and the magnetic force are both related to charges. The word magnetism derives its origin from the Greek peninsula of Magnesia, where certain rocks were first observed around 800 BC to be attracted or repelled from each other. These rocks were most likely lodestone, which is a naturally occurring magnetic mineral. So, just as charged objects can exert forces on one another, so can magnetized objects. Furthermore, we can extend the concept of a field and apply it to magnets. In the electrical case, a charge creates an electric field that fills all space. A second charge placed in that field will feel a force. Likewise, a magnetized object, or simply magnet, creates a magnetic field that fills all space, and a second magnet placed in that field will feel a force. We know that we have 2 types of electric charge, positive and negative, and magnets have something similar. They are called poles. One is the North Pole, and one is the South Pole. However, there is one critical difference. While we can separate positive and negative charges into individual charges, we can never separate a magnet into an individual magnetic North Pole and magnetic South Pole. The poles of a magnet always come in pairs. Consider a common bar magnet, for example. It has both a North and South Pole. If we were to break this magnet in half, we would not end up with a single North Pole and a single South Pole, but instead we would end up with 2 smaller magnets, each with its own North and South poles. Bringing 2 bar magnets near each other reveals the qualitative behavior of the magnetic force. Just like opposite charges attract and like charges repel, opposite poles attract and like poles repel. Bringing the north poles of 2 magnets near each other causes them to be repelled. Likewise, bringing the north pole of one magnet close to the south pole of the other causes them to be attracted. Again, we can think of this force arising because one magnet is sitting in the magnetic field created by the other. One obvious question to ask is, what do the magnetic field lines look like around a bar magnet? We asked a similar question about the electric field lines around a point charge. In that case, we used a second charge, called a test charge, and moved it around the point charge, making a note of the direction of the force acting on the test charge, thereby mapping out the lines of force and thus the field around the charge. We perform a similar action here, but instead of a second charge, we use a second magnet, called a compass. A compass is just a tiny bar magnet, in the shape of an arrow that is free to pivot. It has a north pole located at the tip of the arrow, and a south pole located at the other end. If a compass is brought near another magnet, its arrow will rotate so that its tip, its north pole, points toward the south pole of the other magnet because of the attractive force. To map out the magnetic field of the bar magnet, we just move a compass around the magnet and make a note of the direction the compass needle points, which again will map out the direction of the lines of force and thus the magnetic field. Therefore, the direction of a magnetic field at any point in space is given by the direction of a compass needle at that point. We can visualize the magnetic field quite nicely by sprinkling tiny iron filings around the bar magnet. Iron is a magnetic material and will feel a force due to the bar magnet's magnetic field. Each iron filing acts like a tiny compass and will line up along the magnetic field lines if given a little kinetic energy by slightly shaking them. This helps the filings overcome the static frictional force with the paper so that they can move under the influence of the magnetic force. This simple demonstration reveals the beautiful pattern of the magnetic field lines around the magnet. Notice that the magnetic field lines point away from the North Pole and toward the South Pole. This field is reminiscent of the electric field of a dipole. But unlike electric fields, magnetic fields do not start at North Poles and end at South Poles, but instead must form closed loops. A closer look at the field of a bar magnet shows the field lines continue on within the volume of the magnet to form complete loops. This is a consequence of magnetic poles always existing in pairs. In other words, there are no magnetic monopoles. The magnetic field, like the electric field, is a vector. And just like for the electric field, the direction of the magnetic field at a point in space will be given by a vector that is tangent to the magnetic field at that point, which points along the direction of the field line. The strength of the magnetic field can also be discerned by looking at the field lines. The greater the density of field lines, the stronger the field. Thus, The strongest field around a bar magnet occurs near the poles, where the field lines are bunched up. The further away you get from the poles, the more the field lines spread out, and the smaller the field becomes. As a final note in this section, let's consider the primary application of a compass, which is to guide you in a particular direction as you move upon the surface of the Earth. A compass can do this because the Earth itself has a magnetic field, and we will see later that this field performs a very important function. You probably know from experience that the needle of a compass always points in the northward direction. Since the tip of the compass needle is a magnetic north pole, this tells you the Earth's magnetic south pole is actually in geographic north, and vice versa. The needle of the compass will line up along the magnetic field lines near the surface of the Earth. In fact, the magnetic field of the Earth is very similar to a bar magnet, with the magnet south pole located near geographic north. Drawing a line through the bar magnet creates a fictitious magnetic axis that does not coincide with the Earth's rotational axis. So the location of the north magnetic pole, where this axis passes through the northern hemisphere, does not coincide with the geographic north pole. The two axes are currently about 11.5 degrees apart. It is not well understood what causes the Earth's magnetic field. It originates from electric currents circulating in the Earth's core, and it tends to move around over time.